So yeah, today I'm going to talk about Akka Cluster on Kubernetes. I work on the ops team at Hootsuite. But before that, I was writing a bunch of Scala. We had the fortune to have a reason to use an Akka Cluster, in one of our applications. And so the idea behind today's talk is to get you guys an intro into Kubernetes. So we're going to live code an app, and we're going to run it on Kubernetes. And good intro from Jamie there about how awesome Kubernetes is. And then I picked Akka Cluster to run on there because it's probably one of the more complicated, if not the most complicated, Scala-based deployments you will have to run. Because it needs to understand the state of the cluster. But really, show of hands, how many of you guys are planning to run Akka Cluster or are currently running it on production? Okay, so like not that many. And that's actually probably a good thing because, for what your use case, it maybe doesn't make sense. And how many of you guys are planning or are currently running Kubernetes on production? Okay, so hopefully after this talk, all the hands will go up. All right, so let's get started. So I want to give you a quick intro into Kubernetes. And can everyone hear me if I talk like this? No? Okay. I'll stick to this mic. So Kubernetes sits on top of your data center, and it's really the layer between your app and everything else. And the way it works is it has APIs into basically every part of the cloud, and it runs on all your nodes. And so all you need to do is submit your app to Kubernetes, and you're like, here, I need this many nodes running. I want a load balancer. And Kubernetes is going to figure out how to do it all for you. And so you don't really need to think about the underlying infrastructure. You really just need to think about running on Kubernetes. And that's what's so awesome about it. The way it works, if you want to understand, is it runs 3 controllers, which are basically the control plane for everything. These are going to be running there's 3 of them because it's HA. And this is basically your API into the cluster. You don't really talk to anything else in the cluster. You just talk to these controllers, and it figures everything out. It's running etcd on the back end for its distributed consensus data store. And then the nodes in your data center are actually running all your workloads, all your jobs. They just run a couple Kubernetes daemons that let it communicate with the controllers. And so when you want to run an app, they're going to talk to the nodes. They're going to be like, OK, we can find where to put this app. We're going to talk to the app via our daemons. The daemons are going to put your app and start it running using Docker, and then away you go. It also ties into a bunch of cloud providers. And you can run it on any cloud you want. So into Amazon, it does things like provision an ELB for you if you want to expose your service publicly. It'll add volumes to your nodes, EBS volumes, and then if the node dies, it'll bring up the volume somewhere else to match where your pods are running. So little tie-ins there, and also the same for Google Cloud. And you can also run this on-prem. So the other big thing Kubernetes does is scheduling. So you give it your app, and you give it the dimensions of your app. In this case, we're talking about how much RAM it needs and how much CPU it needs. Kubernetes is going to go look out what's in the cluster, what's running on which nodes have capacity, and it's going to schedule your app onto those nodes. So super simple. This is basically what Kubernetes does. It does scheduling of Docker images. It does monitoring to make sure they stay up. And it provides a really, really great layer of abstraction over your cloud and wherever you're running. And so basically all you need to do is think of it like this. Your app is now running on a computer. The computer happens to span across multiple nodes and a very large data center. But really, all you need to do is think about running your app on a computer. So I'm going to give a quick demo of Kubernetes. So Kubernetes works mostly in these via YAML files. So hopefully you guys like writing YAML. So I'm just going to deploy Nginx. I know this is a Scala conference, but this is the very first intro into Kubernetes. So what I've done here is I've defined a deployment. So this is telling Kubernetes, I want one replica of a Docker image called Nginx running, and I want to expose on port 80. If I just deploy this part here, it's just going to start a Docker image running in my cluster of Nginx. That's good, but usually Nginx, it's a web, so we want to be able to route to it. So this part here gives me 2 things. It gives me a DNS entry called Nginx, and it also gives me basically a miniature load balancer. So as things come and go behind the scenes on this deployment, if I update the deployment, this load balancer, the IP address that we get from the DNS entry is going to remain the same, so we can cache it. And here I'm just pointing this mini load balancer at anything that's labeled with app Nginx. In this case, this deployment up here is labeled with app Nginx. So it's going to route to that. So I'm going to start up some things here. So the Kubernetes cluster I'm using right now, I spun up in about 3 minutes in Google Cloud Engine. So Google Cloud Engine has managed Kubernetes, which makes it really easy to use. So here we have in the cluster, there's only one thing running. It's a bounce box that I'm using. And then I'm just going to attach to that bounce box. And so now I'm going to be able to ingress into the cluster. So now we want to deploy this nginx thing. So we just call kubectl apply. We pass it the directory, the file. So Kubernetes works on these kind of reconciliation loops. So it has the idea of what the state of the world should be and what it actually is. In this case, we told it the state of the world should be one nginx running. The state of the world wasn't one nginx running. It took action to reconcile that. It found a node, scheduled the Docker image on it, started it, made sure it was up, it made sure it's running, and now we have nginx running. So if everything worked, we should be able to curl nginx here. So now you have nginx running. So that's pretty simple. So let's just scale it. So I'm going to scale this nginx deployment to 3. Kubernetes is going to notice that I'm supposed to have 3 running, I'm only running 1. It's going to schedule these onto the 5 nodes that I'm running right now. And then it should be still good. Everything works here. And also, if I scale it back down to 1, this should still work. So everything's updating dynamically with that service IP. The final thing I'm going to show here is a no downtime deployment. So I'm going to run in a while loop. Do curl -i and -s so we don't get all that annoyance. And then I'm going to also do uppercase S, which means I don't silence the errors because that would be cheating on this demo if it's no downtime deployment. I'm going to curl nginx. I'm going to grep for server, which tells me the current version running. I'm going to echo, I think, to get a new line, sleep for 0.5 seconds, and that should hopefully run. Cool. So now we're running on nginx version 113. Let's scale this back up to 3 so we get can see the rolling deployment. And I'm going to go to edit nginx here, and I'm going to change the Docker image it's running. So right now it's running nginx latest. So I'm going to go in here and I'm going to change it to 112.1. So what Kubernetes is going to do here is it's going to do a rolling deployment. So you should see kind of like some 112 nodes come up, then 113 is still running. It should shut down the 113 and bring up fully running on 112. So you can see it happening back here, and now we're running on 112. So that's just a really quick intro into Kubernetes. So the question you guys might be asking, since this is a Scala conference, is why do I care? It's a good question. So the main reason I think you guys should care about Kubernetes is that operational realities affect how you write code every day at your work. Let me give you some examples. How many of you guys are moving to microservices? Put your hand up. Okay, sweet. So same with Hootsuite. We started moving about 2 years ago. We were super stoked. We found a feature. We're like, the next feature, we're like, okay, this is going to be an awesome microservice. And then we're like, actually, how do we deploy this microservice to production? Well, we're in Amazon, and right now we kind of have some security protocols in place, so we can't just spin up our own nodes. So let's ask the ops team to spin up a server for us. And then every single team at Hootsuite did this on the same day. And the team of ops of 5 people were like, yeah, we're not going to be able to get that to you, tomorrow. And so, at Hootsuite, we're taking about 2 weeks to a month just to get all the infrastructure provisioned to run a new microservice. So how does this affect the code you write? Well, say you have a feature coming up, and you're like, this really does make sense as a new microservice, but I can't wait 2 weeks for it. So I'm just going to add this feature to an existing microservice. That's a rational decision. You're going to make the decision over and over again. Suddenly your microservices are getting, kind of big. They become new monoliths. Another example is even when you decide to make a new microservice, you might want to actually split it up into multiple microservices. Maybe it makes sense to have one thing putting events onto Kafka and one thing reading from Kafka. Really, those two could be completely separate. They might want to be scaled separately. It makes sense to have them as separate code bases. But are you going to bite the bullet of an extra 2 weeks on that project, an extra month on that project, just to get the infrastructure to run it? Probably not. So you're going to write that out all in one code base. And you're going to have all the problems that come from having things that don't make sense together. So if you're doing microservices, being able to deploy things on Kubernetes really quickly is a really big benefit and actually lets you write better code. Another example is we're at this conference. We're going to hear about all this cool stuff like gRPC, Cassandra, event sourcing, CQRS. You're going to be stoked to go back and try this. You're going to be like, look guys, I heard about Cassandra, CQRS. It really makes sense for my business domain. All I need is a 5-node Cassandra cluster in 3 different environments. And your ops team is going to be like, yeah, okay. We're going to take a while on that. With something like Kubernetes, You can deploy these things, you can mess around with them really easily, you can run them fully in production, and you can get started and try out new tech really quickly. So as a developer, it's really great to actually have this kind of deployment environments, and it actually does matter to the code you write. Another reason you should care about Kubernetes, or something like it, is this. So who's seen this? This is the reactive manifesto. So Jamie was talking about reactive. This is it right here. And there's two parts to it, resilient and elastic. So this is kind of a clickbaity, but I would say if your infrastructure isn't reactive, then neither is your application. So great, you have this app, it can totally deal with downtime, it can degrade gracefully, but you're still waking up at night to restart the node. And yeah, like your app degrades gracefully, so it circuit breaks and it tells the user like, sorry, something's wrong, but you can still use this button over here. But your user's still mad because your app is broken, right? So even if you have this beautiful reactive application, if your underlying infrastructure isn't reactive, if you have to log in, reprovision a node, spin up a new one, it takes like hours to just get back and running, you're not really realizing the full benefits of having a reactive application. So what we're going to show you with Kubernetes is how it does self-healing, how it does auto-scaling. You can kind of get some of these things in your apps. So this is the second to last slide, and then it's going to be all code. So the app today we're going to deploy is an Akka cluster app. It's going to be really, really simple. We're going to have some sort of LB on the front. It's going to send HTTP requests to the front-end nodes. The front-end nodes are going to process that request, and it's going to send it to the back-end nodes, which are doing some highly intense machine learning to figure out whether or not the message I sent in was talking about a hot dog or not. So if you look at this architecture, and so these nodes here are all going to be part of Akka cluster. So the first thing you should think of when you look at this architecture, and this kind of speaks to what Jamie was talking about, was that why the heck am I using Akka cluster for this? It absolutely makes no sense. Every node here could be completely stateless. You could put a load balancer in here between the backend nodes. You could scale them up and down dynamically. You're done. Walk away. Don't use Akka cluster if you don't need to. And I think that's a really good thing to take home is like, Akka cluster is actually quite complicated. You actually need to understand the membership of all the nodes in your cluster. Out of the box, Akka cluster is kind of a little bit broken. If a node suddenly dies, the cluster won't do anything until you manually say, okay, yeah, that node can leave. Unless you automatically turn on automatic downing, which in the documentation says, do not turn this on for production. So then you're like, okay, what do I do? And then they're like, well, we have this thing called the type-safe reactive platform, which costs you money, and we have a split-brain resolver, which will auto-down nodes without ruining your cluster. So out of the box, it's a little bit hamstrung. So be careful with it. But anyway, we're going to go ahead because it is it's really cool. If you have a use case for Akka cluster that makes sense, it's a beautiful piece of technology, and it saves you writing a ton of code. Okay, so this is the sample app we're building. So the first thing we're going to do is we're going to add roles and routers. So what do I mean by this? So I want to be able to scale up and down these two nodes, these two types of nodes separately. This intense machine learning happening here might be more CPU intensive. I might change the machine learning. I might want to scale that workload differently. The front end nodes, they're doing HTTP. Maybe I'm getting DDoSed. I want to scale those up, but actually they're cutting off all the calls to the back end, so I don't need to scale up things at the same time. But I want to keep the same code base. So the case classes that I'm using to send messages between my actors here, using Akka remoting, I don't want to duplicate them. I don't want to have to serialize them in two different ways. I mean, you should be using protobuf if you're sending things across the network here, but the point still stands. And so I want to use the same code base for all this. I want to be able to develop it. I want to be able to deploy it all at the same time. So Akka has this idea of roles. So you can mark a node of having a specific role, and based on that role, you can spin up specific actors on that node. So we're going to use that. The other thing we're going to do is routers. So Akka cluster has this awesome thing called cluster-aware routing. So these front-end nodes, they don't care where they send their data. But I'm going to show you the code, and we're using just regular Akka actor sends. And so the cluster-aware router on here, the front-end node thinks it's sending to a local router, but in fact it's sending to a local actor. But in fact it's sending to this router, which is going to know when nodes get added to the cluster and leave the cluster. It's going to automatically update what it sends to. And so it's going to be heartbeating these nodes, and if they die, it's going to stop sending things to them. So this is a really cool benefit of Akka cluster. With Akka remoting, yeah, you can send things across the network, but you need to specify I'm sending here, here, here. With this, you don't have to worry about it. Akka cluster handles everything in the back end. And then we're going to get to seed nodes. So this is the last slide. So let's walk through the code. So let's talk about these front-end actors. They're super simple. They're going to take a request from the back end, or from the HTTP front end. the not hotdog requests, and they're just going to forward it to the backend. The backend is passed in here as a simple actor ref. And here's the beauty of Akka Cluster. This actor ref could be local on my JVM, or it could be completely across the network. It could be this, and when I'm running across the network, it's actually going to be that cluster-aware router, but the code remains the same. So front end is really simple. Look at the back end, a little bit more complicated. This is the sophisticated machine learning I was talking to you guys about. It's going to take in that request there. It's going to determine whether or not we're talking about hot dog, and it's going to send the result back to the sender. And I'm also going to be logging the host name here, so you can see as I dynamically scale these that it's actually coming from different nodes. So those are the two simple actors, and then the boot class is a little bit more complicated. So this allows me to dynamically inject which role I am using. So if you look at, usually you specify your roles like this in your config. So by default, it's going to be using both front end and back end roles. But I want to use the same code base, but I want to have different things happening. And so environment variables are a great way to do that. And so this allows me to inject the cluster roles as an environment variable. And depending on that, I'm going to do different things. This is just all that Akka cluster goodness. Here I'm starting the cluster. So here I'm just seeing whether or not I'm a backend or a front end. So if I'm a backend, I'm just going to run one backend actor. Here, it's going to be called backend. If I'm a front end, I'm going to do a little bit more. I need HTTP and I need to send things to the backend. So here, if I'm a front end, I'm going to initialize that backend router that I was telling you guys about. It's going to use role backend. This means it's only going to send messages to nodes in the cluster that have the role backend. And because the cluster is aware of all the nodes, it can do this. It's going to send to the /backend actor, which we started here. And this just allows us to run those. If I'm running on only one node and I have the same role on the same node, if I have both roles on the same node, then this allows you to send to yourself locally. And this is all about, like, if I can dynamically scale this up, it can go to a max of 1,000. So that's good. So this just gives us an actor ref. And we're just putting that into the front end there. Finally, we get to Akka HTTP. So we're going to be taking requests on slash. We're going to take the message parameter. We're going to package it up into a not hot dog request. And then we're going to send an ask to the front end, which is going to pass it to the back end, which is going to return a response. And depending on if it's a hot dog or not, we're going to return that. This is for health checking. I'll talk about that later. We bind to port 8080. We shut down cleanly. And that's the end of the code base. And so, see how you have these case classes here. You'd probably want to protobuf encode these if you're actually doing this in production. But the cool part about Akka cluster roles is I can use this code base even though I have the two actors are actually running on separate nodes, and I just share the same code base. So let's just make sure that all works. So I started SBT already. So right now it's saying leader is moving node to up. So since there's only one node in this cluster, everything should be working. I should be able to curl localhost 8080 and ask, is this about a not dog? And yeah, it's saying, yeah, this isn't about a hot dog. And if I ask about a hot dog, it says, sweet, yes, I'm a hot dog. Okay, so we got something running here. Now, that was running on only one node. So if we go back to this code here, we have this thing called seed nodes. So you're talking about a cluster. When this node comes up, or when a new backend node comes up, how does it say, hey guys, I'm here? Well, it needs to know something to talk to. This is where seed nodes come in. So this specific configuration here, I'm hard coding it to being localhost 2551, which is the actual JVM that I just spun up. And so when it notices it's talking to itself, it's like, okay, I'll form my own cluster. Now, when you're running Kubernetes, you're going to be coming up on random IP addresses. So this hard-coded configuration isn't going to work. Luckily, this guy, Heiko Seeberger, wrote a really nice Akka extension that uses etcd as a way to discover all the other nodes. So when a node comes up, it's going to talk out to etcd. It's going to be like, hey, are there any other nodes in the cluster? If so, it's going to join them. If there aren't any, it's going to take a lock. It's going to start to form its own cluster. This is to prevent kind of split brain when two nodes come up at the same time. It's going to form its own cluster, and then all the other nodes are going to join that cluster. So this is a really simple way to get kind of this dynamic scaling working. So that's all you need to do. You just include this extension, and here's a config for it. By default, it uses etcd. You can also use console and zookeeper. And we're going to assume that etcd is running on localhost 2379, but if it's not, we can inject an environment variable to actually point to it. So if I run this right now, it's going to break because I'm not running etcd on localhost 2379. So what you want to do is start etcd. So Docker is great for this. This is just going to start etcd image running on my laptop, and it's going to publish its port to localhost 2379. And I already have it running. So let me just kill it. Cool, so let me go back to that. So now I have etcd running locally. I should be able to curl it. Good, so it's running. So now when I run this, it's going to notice that there's no seed nodes defined. It's going to talk to etcd. It's going to find that it's the only node in the cluster, and it's going to move the node to up. And I should be able to curl hotdog, and everything seems to be working. Okay, so now we have this running locally on our laptop. That's awesome. So we've got the roles and routers working, and we got the seed nodes working. Now we need to package it into a Docker image in order to get it running on Kubernetes. So packaging Java into Docker images has some gotchas. So if I go to, where did I put this? Presentation script. Yes. So if I run Docker normally, so here I'm running Docker. I'm telling it I only want 100 megs of RAM. I'm running the OpenJDK version 8131. I'm just running Java- version and then show settings. So like I told you guys about how Kubernetes does scheduling, it needs to understand the dimensions of what you're scheduling, which means best practice is to specify how much RAM it's using and how many CPUs it's using. So here I've told it it's using 100, and the JVM's like, okay, sweet, I have 400, right? So what's going to happen is Kubernetes is going to kill it because it's using more than it's supposed to. So what's going on here? So JVM isn't cgroup aware. So you can actually, in a Docker image, you can find out what's on the system. You just look at /proc. That file system is still available. And so that's what the JVM is doing here. Luckily, they backported some stuff from Java 9 into this version of the JDK. And so if I run with this, experimental options, so we're using unlock experimental VM options, use cgroup memory limit for heap. Now it's going to work. It's saying, okay, I only have 44 megs. So you're like, okay, sweet, let's go to prod with that. But what if I'm not running 100 megs, because who does that? What if I'm giving it a gigabyte, because this is Scala, you know? Okay, well now it's only using 200 out of it. So what's that 800 megs doing, right? That's a complete waste of space. So Java's being nice here. It's thinking it's running on a shared system, but it's not. It's going to run in a Docker image completely. So we want it to use literally everything it can grab. So here we add an additional option which says max RAM fraction equals 1. And now it's going to actually use the right amount, 910 megs. So this is available now in Java 9, and also it's backported into this version of the JDK. So if you guys are running in Docker, I recommend it. If you don't have that version or whatever, you just have to specify -max RAM, but that's not as nice. So we need to package this image up into a Docker image. So let's use SBT assembly to build us a nice big fat jar. And then let's look at this Docker file. So Docker file is what is like a build script for Docker images. So from is the base image we're using. So this make sure we have Java installed. We're going to add in this target that I'm just compiling above here into app.jar, and then we're just going to execute it, java-jar app. And this is all that stuff that I was showing you guys earlier to make sure that we're not going to run over our memory limit. So we're going to do docker build dot, and we're going to tag it to, actually I think I have this in my history. Yeah, we're just going to tag it Kysow Akka cluster. Boom, super fast, we now have this built. So let's test that this works locally before we go crazy. Now, we know that we need etcd running. When you guys are running Docker for Mac, it's actually running in Xhive, which has its kind of own network namespace. So even though I'm running etcd locally on my laptop, it actually can't talk to it. It needs to use like port 192.168 or something. Anyway, it's a bit annoying. So what I'm going to use here is docker compose. So this says I want to run 2 Docker images etcd, the same one we were running before, and this new one I just built, and it's going to link it to etcd. So even though it's running in the top Docker namespace there, it can still talk to etcd. So running Docker Compose up, it's going to bring up both those, and we should be able to curl everything normally. Okay, so it says leader is moving node up, curl it, everything still works. Okay, so we got this Docker image, we're good, it's good, it works. Let's push it up to the registry. So we use Docker push to push this up to the registry. And then we're going to go into Kubernetes. So let's look at what we need for Kubernetes. So the first thing we need to do is we need to run etcd. So just like the Nginx deployment, see how similar it is with etcd. Like I said, Kubernetes is all YAML files. I hope you guys like writing YAML files. You can endorse me for YAML on LinkedIn. That'd be great. So I have etcd running here. A couple of options to tell it where it is. It's running at 2379. So like I said, the deployment just gets your app running, but it doesn't give you a load balancer. So this service declaration says, hey, can you give me a DNS entry called etcd? And 2379 should map to 2379 and route to anything that's labeled app etcd, which this is. So let's just apply this to the cluster. And let me just kill Nginx. Cool, Nginx is shutting down there. So I'm going to use kubectl apply -f, says point me to a file, and I'm going to point it at etcd. Kubernetes is going to do that reconciliation group. It's going to be like, okay, it should be running etcd, boom, etcd is running. Now in prod, you're going to be running more than one etcd, but I didn't do that for this demo. So we should be able to hit etcd on health here. So this DNS should work, and it does. Okay, cool, so now we have etcd up and running. Now let's deploy the app. So the app's a little bit more complicated. So if you go back to the architecture here, we wanted to be able to deploy the backend and the front end nodes with the same code base. That means with the same Docker image. But we want to be able to tell them, hey, you are a front end node, and hey, you are a backend node. And we also want to be able to scale these separately. So the best way to do this in Kubernetes is to create a new deployment for each of those. So here we're creating the front end deployment. It's going to use that Docker image I just built and just pushed. And I'm going to inject a couple environment variables to it. So in Kubernetes, each pod is a collection of Docker images. You can think of it just as your app. Each app gets its own IP address. This is really, really powerful. And it's really, really useful for something like Akka Cluster. So we need to inject that to tell it, hey, this is your IP address. And then if we look at the code base, we're just using that pod IP to override hostname if it's available to us. So that's simple. The other thing we need to know is what role we are. So here I'm just injecting front end for the front end nodes and back end for the back end nodes. The front end nodes are available on port 8080, and the back end, and so they also need the Akka HTTP, or sorry, Akka remoting port 255.1. Here I'm setting the dimensions for my app. So the requests, this is how much it needs. So 0.5 CPUs and 512 megs of RAM. And this is like how much it can spike above before Kubernetes is gonna be like, okay, you're taking way too much, I'm gonna kill you. So this is all we need. And we also need this probes here. I'm gonna talk about that later. But basically this is just so Kubernetes knows that you're alive, so it can actually add you to the load balancer, so it can route traffic to you. If you don't do this, Akka HTTP takes a couple seconds to start up, and so it'll be routing traffic to a dead port. So that's the front end. That gets us these 3 nodes. Well, 1 right now. And then I'm creating a service on the front end, because I want to route HTTP to this. So here I'm calling my service not hotdog. It's going to route to any node labeled front end, and it's going to take 8080 and wrap it to 8080. So sweet. Now we need the back end. So these nodes right here. Back end, almost the exact same as the front end. It's going to be called something differently. It's going to run the same Docker image. It's going to inject the same pod IP. Here we're changing the value of a cluster roles environment variable to be backend. And also running on 255.1, we use the same amount of resources, but we could scale this up separately if we wanted to. And then up here we're using a health check, an HTTP health check on port 8080. That works for this, but the backend isn't running any HTTP, it's only running Akka remoting. And so we're using a TCP health check on port 2551. And so this should get us going. So that is the deployment. So I should be able to run this. So it's going to create the front end deployment, the back end deployment, and that service so we can route to it. You can see the nodes are 0, 1, so this is waiting for the health check to succeed before it says it's ready. Okay, so if everything worked, I should be able to go curl not hot dog on port 8080, send a message called hot dog. Okay, how many people think it's going to work? Oh, there's not a lot of enthusiasm there, but look, it did work for all you doubters out there in the audience. And so I can also hit it with this, and so now you can see that we're routing from the same front end, 855, and from the same back end, because we only have one of each. Okay, so this is kind of cool. We just got Akka cluster running on production, well, my production, in a couple minutes. The Google Cloud engine let us spin up Kubernetes really fast. It let us spin up Nginx, etcd, these different Akka clusters. Everything came up really fast. So that's really nice. So when you're talking about how long it takes to get these things running at your organization, something like Kubernetes can get you up and running really quickly. So now we're going to mess around with this because we want to talk about kind of we want to talk about how it helps with the reactive manifesto. So I'm going to run a loop here. So while true, do curl. We're going to curl S to silence that progress. S won't silence the errors. And 1.5 is going to give us a timeout of 1.5 seconds. We're going to curl not hot dog on port 8080. We're going to send a hot dog message. We're going to echo to get out of there. We're going to sleep for 0.5 seconds, and then we're going to keep running here. Okay, so this is just going to run here. And you can see that it's coming from the same hosts because we only have one of each. So let's scale it. So I can run kubectl, scale. We're going to scale the backend first. Why not? Give it 3 replicas. What's going to happen here is the backend nodes are going to come up. They're going to talk to etcd and be like, hey, where's my cluster? They're going to register themselves in the cluster. The cluster aware load balancer is going to be like, okay, sweet, I have more things to backend to route to. And so you should see here the backend now is changing. The front end remains the same, but the back end is now routing between all of them. And if I scale it back down, this is really the hard part. It should cleanly leave the cluster, deregister from the cluster aware load balancers, drain its traffic, and go back to one node. So that's working. So now you have this dynamic scalability. So the Akka clustering application that we built at Hootsuite is really awesome. We used it for Twitter streaming, and there's a lot of persistent TCP connections going on, and it was kind of complicated, and Akka cluster was a perfect thing for it. But we started to get too much traffic, and we're like, okay, let's scale the nodes. We need more, right? This took about maybe 1 week. So we need to bring up a new node. We need to make sure it's part of the autoscaling group. We need to provision it with code. We need to update all the code so it knows where everything else is. So with this, you can bring things up and down really quickly. So it makes you can be a lot more agile. So that was the back end. Let's scale the front end just to show it works. This one's a little bit different because it needs to add itself to the load balancer. And this is where that health checking I put in is key. So this is taking too long, so I took this out. But if you don't have the health checking, you hit the port 8080 and you get connection refused. Because the Docker image is running, but Scala hasn't booted yet. So here we're routing between the different front ends. So that all works. That's cool. Okay, so we got Akka running here. We're pretty happy. But what about that whole elastic scaling? I don't have to watch. There's a top command here, which can tell you what's using what. But I don't want to have to do this manually. I just want it to scale up automatically when my app becomes super popular because it's featured in a TV show. So what I'm going to do is use auto scaling. So I'm going to say I want you to auto scale the front end nodes. I want a minimum of 1 running, max of 5, and I want a target CPU percentage of 10. And actually, let me just scale this. Deployment back down so you can see it actually moving. Auto scale. Yeah, 10 obviously is really low, but I want it to do stuff. And we're going to do the same for the back end. Okay, so now we have this auto scaling set. So they're called horizontal pod autoscalers, HPA. So you see here, it doesn't really know what the CPU is right now. It's collecting that data, but it said this is a target is 10%. Now we're not hitting it with any traffic, so unless it's doing something crazy, it shouldn't be complaining. So we need to hit it with some traffic. So let's do it. So this is called slow cooker. I should really use Gatling, but here we are. We're going to hit it with 10 threads running 300 requests per second, and it's going to report to us back every 5 seconds, and we're just going to hit that same endpoint. Here we are, we're just running 3,000 requests per second, and hopefully, okay, so we should see kind of this CPU usage sped up here. So you can see that it actually isn't, it's kind of hard to see because of the thing, but it's trying to run 3,000 requests per second, and it's reporting every 5 seconds, so it should be getting up to 15,000, but it's not. It's only getting up to like 86. So there's some contention, probably CPU, because we're just absolutely like hammering these two nodes. So hopefully this reports in every 30 seconds, so you have to stick with me. Hopefully this should start to scale itself. And I have another video, so I also added in auto scaling to the cluster itself. So the Google Cloud Engine should like recognize that, hey, like I don't have enough nodes to schedule this on, because I only have like 5 nodes right now, and so it can actually auto scale the cluster. So if you have a lot of workloads, you might want to turn this on. Okay, so hopefully this works. And if it doesn't, then that's okay. Come on. Unfortunately, in the Google Cloud Engine, you can't. There's a parameter that says how many to run, how often to check in to your autoscalers to make sure everything's fine. And in the Google Cloud Engine, you can't actually specify this parameter. Okay, there we go. So it's recognized that it's not running enough, and it's starting to spin up all these nodes on the back end. And everything should be fine. So there should be no errors into the actual, this number right here is how many successful requests there were, and this is how many failed requests there are. So there's still no errors, which means that Akka cluster is properly like adding all the routers and everything. And here we are, it's all running. And then some of these nodes are in pending because I don't have enough space to run them, because like it can't schedule the nodes because I don't have enough CPUs in my cluster. And so what will happen is they'll just sit there in pending, and then if I turn on auto scaling, it should all auto scale itself properly. Okay, so that's kind of the end of the demo portion. Let's get back to the slides. So what did we just do? Well, we got Akka cluster running in like half an hour, which is great. And we kind of proved that you can deploy things really quickly with Kubernetes. And I hope I convinced you guys that having the ability to do so actually makes a benefit, makes a change to the actual code that you get it right every day. Because you get it right, small services, and you can deploy them in production quickly, and you don't get battled back from all your product managers saying, well, why, it takes a month, like, can't you just add this to the old service? That's how it worked the old way, right? So being able to deploy things quickly, especially something as complicated as Akka cluster, can really make a big difference to your organization. So this is all available on GitHub at Kysow and that right there. And thank you very much. Do we have time for questions?
Yeah, we have time for a couple questions.
Sweet. Any questions? Yeah, go ahead.
Can you compare and contrast what you just did versus, say, the split brain resolver?
So yeah, so this what I have right now still has that same problem with split brain. So if I absolutely just kill the JVM on one of those nodes, the cluster is going to be like, hey, it didn't leave, like it didn't tell me it was leaving, and then it's going to mark it as failure, as down. So everything will still work in your cluster. It'll get ejected from the load balancers, but then you actually have to manually go in and be like, yeah, I know this thing is dead, like either by JMX or HTTP call, like, okay, actually kill it properly from the cluster. So what you would want to turn on is like auto downing, which will be like, if it's dead for a certain amount of time, actually like exit it from the cluster. Because while it's in the state where like a node's unreachable and it thinks it's dead, it won't actually let you do anything. You can't add new nodes to the cluster. It's just really frustrating. So I actually haven't solved that problem in this specific case. So you'd have to either use like the split brain resolver, or you'd have to have something, you could turn on auto downing, and things should work pretty well because you have etcd as kind of like your seed node. It understands what's running, so you shouldn't get split brains. But I haven't tested it out. Yeah, it's kind of one of those complicated things with Akka clustering that burned us at Hootsuite. We actually had a network partition between an AZ, and we had quorum set, and we thought we were good, even though we had the split brain resolver, but we didn't have enough quorum in both sides of the split brain, and the whole cluster just like, okay, well, I'll shut down, and we were burned by it. So it is really complicated. Yeah, any other questions? Yeah, go ahead.
Last time I explored Kubernetes, I noticed that you can auto scale your nodes on AWS. Has that changed?
Sorry, you were saying that that last time you tried Kubernetes, you couldn't scale the nodes?
I couldn't scale the underlying EC2 instances.
Yeah, I understand. So if you're on Amazon, I think it's experimental now, the integration into, the question was, can you scale the nodes on Amazon? In Google Cloud, it works, although it actually shuts down like your control plane for a while, so it's not that great. But on Amazon, it does work. I think it's an experimental feature that will auto-scale the nodes, but I haven't tried it yet personally. But you could also scale the underlying like auto-scaling group you're in, and everything will work because the nodes will register with Kubernetes. Sweet. All right, well, I'll call it there. If you want any questions, you can talk to me afterwards. And thanks a lot, guys.